This is the third program based on the modelling game. This time we're going to focus on the process of writing reports. The particular problem we've given our two teams is based on examining what sort of shaped heaps you get when you pour different materials. So the materials we've got in the studio have all formed cones, and we're asking the teams to produce a model that predicts the angle at the top of the cone. Now, measuring angles on these sort of heaps takes quite a while, so to help the teams, we've made a single measurement of the angle, and we've made an estimate of the error in that measurement for them. So now what I'm going to do is give the team a specification, and this specification emphasizes to them that we want them to report back what form of model they get, and also report back how one would use that model to make predictions.
Thank you. Right. Lots of fun. I'll read it in reverse order. The different types of sand on the set have been poured to form conical heaps. The angle alpha for each heap has already been measured. Your task is to write a report which would enable a third party to predict the angle alpha for some sand in their possession without directly measuring alpha. Your report should also explain why the conical heaps have the angles they do. So there we are.
In the first 20 minutes, the blue team decided to work on a feature list.
We've decided that the shape is a cone.
Yes, sir.
I think perhaps I should say shape is a cone. So we've taken that into account. So let's write down that's our assumption 1. This is our assumption 2. Roughness of the surface, that's saying something about that there is friction there. Hold it together. Now, we haven't said anything about the size of the particles. All that we've said is that they will be spherical. Haven't said anything about the weight of the particles, because we reckon that they'll be, well, I mean, if we know the size, we can certainly work out its volume, and so we can work out its weight if we have the density. I'm not so sure how important these are going to be initially till we get started, but we'd have to come back for them. If we were going to do a dynamics model, or, you know, a statics model based on mechanics, then we would have to take these into account. My feeling is that it might be better to get a geometric model.
I think the geometry is the thing that, that I feel I want to get to grips with.
Because I can't do geometry. This dry friction, in a sense, it's got to be there to hold it in the shape. Yes, but to quantify it is going to be difficult. And again, if we're thinking geometrically, this is mechanics, this is mechanics. So that could come into a mechanical model.
The yellow team also start with a feature list.
Coefficient of friction of one grain on another.
That sort of thing, yes. I'm not sure if one can define it in the text, as in the textbooks there.
Anything else?
The only other thing I would think about is the speed at which it's poured. Whether that would affect things.
Yes.
The yellow team took their own measurements of the cone angles.
120 is a nice sort of number.
Yes.
You wonder why it's just a little bit below that all the time. 120 would be a nice number for it to be.
120, one might imagine there'd be a geometrical reason for that.
Well, have we tried...
Maybe we should go back to our feature list.
Yes.
And have a look at what we think is becoming important on this. Because we've worked with various sizes,
Right.
and they didn't seem to make a lot of difference, I don't think. So, to my surprise, really, this is not very important.
Size is the one that we would expect, I would have expected to work with. I mean, I don't think we should give up straight away.
Well, we expected that.
It's getting a very elaborate notation, that, isn't it?
Well, we expect it to be important, but it doesn't seem to be.
Yeah. Okay, shape,
Well,
we haven't worked on shape.
Shape, again, there were a variety of shapes there.
Yeah.
Flat gravel to pretty round aggregate. I suppose the sand was a variety. Doesn't seem to be terribly important. In fact, you go through all these things and nothing much seems to be terribly important.
The only other thing that can be important is the geometry, the actual geometry, inherent geometry of it all.
To investigate the geometry, the team makes the simplifying assumption that all the particles are spheres.
You've got a pyramid almost there.
I wonder
You've got a face that side, a face that side, a face.
Yes. But that's a very regular one. I think it would be interesting to see if this was also around about 120. Those aren't regular, those are much more random. So.
Okay.
Well, once again, which one?
Just to see that we're not doing anything that's too dissimilar.
I wouldn't touch it.
Well, it's difficult to...
Well, do a projection on it. Put the protractor about there. Just
I think that's less.
We ought to be able to work this out first. I mean, it's a regular...
yes. It's 120, it's 60-degree triangles. It's a tetrahedron.
Now they consider the variation in sphere size against the angle at the top of the tetrahedron.
But I think that's going to be 60 degrees, isn't it?
No, because 60 degrees on its side.
60.
But it depends which way you look. It's going to be... If you look from this direction, it's 60. That on that face. An equilateral triangle there.
Perhaps you ought to draw a diagram.
Yes, but the equilateral triangle is slightly slanted, so it's a projection of the equilateral triangle, so it will be more than 60.
It's not going to be as much as 90, is it?
No. But if you have 60 degrees to start with, then you can't have over.
We need to draw a diagram of that, don't we? I mean, it's just a regular tetrahedron. And
it can be our first model.
yeah. It doesn't look as though it's going to be all that
Doesn't look very successful, but it might give us something to think about. So maybe we should go and encapsulate that particular structure, which is probably the smallest angle we could actually have, I imagine, and work out what that angle is.
After drawing a diagram, they then look at the process by which spheres form into heaps.
Of course, they're not all going to be full, are they? I mean, if we could... That's a point, what you've just done in shaking it. If we could actually build a structure where each of these... There's a space for each of these balls, like there, and if we could very carefully by hand fill them all, we get a very shallow angle. But they're only actually filling at random, and some of these are missing. You can see it here, that some of these are missing. And then you get a much shallower angle because there's actually a ball missing here that could go towards making a steeper one.
Yes.
Then they consider how non-spherical particles fall.
Well, it'd be difficult to measure it, but you could say it would be more than 90 degrees. It's sort of... It might easily be similar to the angles we've had before.
Can we
Certainly not
attack it?
60 degrees.
Can we attack it from trying to say what was wrong with our original model?
Yes. I think what was wrong with our original model was that we actually packed them in by hand in the closest fitting arrangement.
Right.
And what's happening is these things are coming in more or less at random. They're hitting the middle and they're rolling down. And they're filling spaces more or less at random. But there are gaps still.
The blue team also started by considering a packing model for spheres, but then decided to base their model on friction.
Can I suggest going over to a mechanics type model? Obviously geometry, all we're going to do is we're going to say we're going to have to pack them in some way, and the packing depends on the angle, and we're going to get a thing then which is independent of the size, which is okay. If we could get 115 we'd feel confident, but it really depends on the packing that we're assuming. Could we do possibly a mechanics type model where we've got an inclined plane, all right, which represents the side of the cone? We put a particle on the inclined plane, and the point at which that particle is about to slip would be the angle of the pile. Do you understand what I mean, John?
I understand what you mean.
Yes.
For that we need
Coefficient of friction.
Yeah.
That would need coefficient of friction.
who wants to know the angle of a pile of sand anyway? It's the volume that I want to know when I have my sand delivered to make sure that I haven't been done.
Yes, you'll want to know if you've got room on your drive for the pile to be piled.
Yes, I don't want to know the angle. I want to know how, if I've got a volume of sand, what the diameter of the base will be.
Or we can tell them
But once you know that, you can work out the
It
angle.
always
I mean,
stays on
isn't
my
it?
drive
It's
because the garage stops it going.
Do you think we could...
Right, well, we've destroyed the problem. Let's find out. A silly problem.
Yes. One always says it's a silly problem when you can't do it.
do it,
Yeah.
How can we find
It's a sensible problem when
the
you can do
coefficient
it.
of friction?
Well, you could have an inclined plane and raise it till it starts slipping, and that would give you the coefficient of friction.
It shouldn't, should it?
Yes, it should, because then it's sliding on itself instead of on
Yes, of course.
the sandpaper. Let me get my hand, my elbow down again. Right, up we go. Now that's running quite... There we are, it's moving now. Okay, give it a quick measure.
Try again. 36.
They then outlined their report based on the models they developed.
It was what Mike termed a close packing problem. And I think as Mike observed, and probably as we felt at the beginning when we were a bit depressed about it, that it was a bit difficult.
Yes, he didn't really give the right answers. And
Well, we didn't seem to get anywhere, did we? We couldn't really cope with the geometry to start with. Well, now, what were our assumptions for this particular model? I think we have them up there. Can you read them?
yes, no, we assumed firstly that all the particles were spherical and had the same size.
So we have the same... I'll just write down a very brief summary, but it will be sufficient for us to put the report together. So, same size spheres.
We assumed that they were piled up in a cone.
So our assumption was that the pile was a cone. The pile of spheres forms a cone. And actually, the geometric model couldn't explain that as succinctly as the mechanics model.
No.
which
We
is
assumed
nice.
that the particles were always held together by friction.
Yes.
So it was...
Yes.
There was enough friction to hold them together and hold them on the base.
Yeah. So
It's really the friction
on the base
I
that's
think,
critical,
the
yes.
one.
yeah, enough friction on the base.
I then discussed with them their criticisms of their final friction model. So this is where we've had criticisms here under revisions. These are actually things that you would hope in the fuller report to have developed. Is that right?
If there was time.
If there was time, yes. But even if there wasn't time, I think we would have thought about what improvements we could make to the model and would at least have said what we would have liked to have done if we'd had more than our specified number of hours. Even if we couldn't do them, we'd try and tell you what we would have done if we'd had time.
The yellow team, after pondering the problem, became unhappy with their first packing model.
We saw this photograph of an actual heap of sand, and I think this showed pretty clearly where we were going wrong, because things weren't as closely packed as we'd assumed. There really were spaces in between the particles that were really quite large.
So they developed a revised packing model.
Here is, in fact, what we're trying to do. We've got a base here consisting of 3 spheres, and they're separated by some equal distance for each one.
Before they were touching, now we've
Before they were
separated
touching, on our first model, these 3 were touching. This time, we're actually going to make sure that there's some more space. That ties in with what we've seen in the picture. And we're going to say, well, there's another sphere actually going to fit in like that, and we want it to fit in such a way that this angle here, this vertical angle here, is 60 degrees. Because then if you have two of those, you've got the 120 degrees that we're trying to get. And what we want to find out is what this distance has to be, this distance here has to be, in order to get that 120 degree angle.
Right, so we did some trigonometry on that. It got a little bit hairy.
Yes, as usual.
Because we were thinking in 3 dimensions.
But in fact, the answer was quite simple when we
Yes.
worked it out.
Yes.
Although perhaps we might go into the mathematics in a little while, but in fact what actually happens is that these spheres are separated in such a way that if you take another sphere and put it underneath, it's now falling apart, so that we have this on.
Shall we hold it here?
Can you hold that?
Yes.
Okay. Now the next sphere fits on top, so that the one underneath and the one on the top actually touch. I think you can just about see the arrangement there.
Writing their report, they list the criticisms of their first packing model.
Criticism is that it was hopeless.
Hopeless.
Because it was approximately a half the right answer.
Okay.
It was miles off.
Well, do you think we got half the marks there?
So it must be rejected. It was nothing
Right.
like right. Must
Well,
be
you
rejected.
could reject it also by looking at the picture that we had. It didn't accord with the picture. I mean, one of the biggest criticisms is that the particles on the diagram that we were given were actually very well spread out, whereas this was far too closely packed together.
So we have to put that down. Didn't agree with microscopic
Evidence.
picture of sand.
Okay.
For both those reasons, we had to look for something better.
Then they report their second packing model.
In fact, we ought to go over these fairly briefly because we've got 2 revisions to the model. We've got 2 different structures.
Okay.
And I think,
So we would talk about Model 2,
right, Model 2.
in which we noticed that the interparticle distances
Right.
were greater in photograph than in Model 1.
Okay.
And we can afford to be quite honest about the way we did this. We looked for the structure, the regular structure, that would give us 120 degrees.
That's right.
And I think we state that. For a regular structure, that would give 120 degrees.
Okay. Now, I think diagrams here are essential because it's a fairly complicated model. Perhaps even a photograph of this model here that we've had.
Yes, but do you think they would send the balls to the tutor? I mean,
All right.
yeah, the little
I
model.
think a photograph just of that would be very useful, and also a couple of views of this so that you can actually see what's going on.
It's very difficult to draw. You'd need a number of diagrams. Here is one looking from the front.
Right.
You'd certainly need a plan view, which we drew, like that, with a ball on top.
Yeah.
And perhaps even something like that that gives a total structure to it.
And that one too
Yes.
would be very good.
Okay.
And then you would get actually into the trigonometry.
The yellow team also developed a third model based on a different principle.
Okay.
The essence of this was it was still close packed.
Still closely packed.
Each layer closely packed.
But narrow angle at the edge.
But it was What do they call those buildings? Zigger...
No, it's stepped.
Stepped. Stepped is the best thing, yes.
And the reason why it was stepped was because to capture particles.
Yes, possible explanation for that. If the structure was formed in the first place, it would be self-perpetuating.
Yeah.
Provided particles were stopped every second.
Right.
I asked the team if their first oversimplified model had been useful. Well, the initial model is interesting, isn't it? Because it was a nice, easy one to work out.
Right.
And you're quite sure it's wrong.
Oh, yeah.
So was that a helpful thing to have done? What role did the initial model play then?
It sharpened our minds because it was a sort of obvious thing to look at.
It helped us to think that we were looking for a structure and that the obvious structure wasn't nearly the right thing to go for.
It led us to then ask what is wrong with this structure, and that led us to increase the interparticle separation. So
it gave you something
to work
to compare any subsequent model with.
I think our aim with this model was to keep things as simple as possible. I think if you don't start with a simple model, you can get into very great complications. So we decided to start with something very simple, and unfortunately it didn't work out. But it did help in the revised model.
I think we were suspecting that it wouldn't work out when we set it up, but it seemed like we had to see why it wouldn't work. If we didn't understand why that wouldn't work, we couldn't make any further progress.
I asked them to explain their interpretation of their second packing model.
But this is where we would claim some success, both in the interparticle distances and in the volume of sand to volume of the total. And we would give some interpretation as to why this number was only 20%, only to within 20% of the right one.
Because if the particles are not of the same size, that's going to increase the spacing.
We think so, because it will fill in.
Increase the density, not the space.
Without affecting the
Increase the
overall
density.
structure.
Increase the density.
Because they'll fill up the spaces.
So the little ones will go into the holes left by the big ones.
We think that might be a qualitative reason, but we wouldn't like to quantify it.
Is there any way one could assess that effect? Any separate experiment one could do?
Well, I think one can argue from the absurd case. If one had big balls and sand in between, you'd obviously increase the void. I mean, that's
and that argument might have been a good one to put in, quite explicitly, mightn't it?
Yes, I mean, I think one would put that argument in this. This hides a multitude of sins, this little sentence there.
Right.